You know, within just an hour of where I am right now are hundreds of manufacturing operations. Large, small, high-tech like this, and low-tech, making consumer products, industrial products, electronics, products for healthcare, arts, mining, music, clothing, food products, housing, transportation, you name it. Each manufacturing process is fascinating to watch and involves a tremendous amount of ingenuity to design and manufacture a product as efficiently as possible. Some are top secret. But let's take a look at a few who did let us inside and try to understand just a small sample of these manufacturing processes, each of them in 6 minutes or less. 80% of TV sitcoms and series, including Survivor and many feature films, are shot using wireless microphones made in this factory.
This is pretty much a hallmark of Lectrosonics products. If you watch Entertainment Tonight, The Jay Leno Show, any news event by networks or call-letter TV stations, this is a wireless transmitter module that plugs into any kind of a microphone with standard XLR connector on it, and it converts the mic into wireless operation. The receiver picks up the radio signal, turns it back into audio, and then sends it into the recording or the sound system chain. This particular one is a compact unit that's used for motion picture and television gathering. Yeah, so a visual inspection is done to make sure the parts got in, placed correctly, that the copper's connected. This part starts out as an extrusion, which is a drawn piece that is cut off to length, and then the machining centers remove the material out of it. This ends up being a front panel for a 4-channel wireless microphone receiver when it's finished. This is the chassis of a wireless microphone receiver. This particular piece is machined out of a solid chunk of aluminum. Probably 50 different kinds of wire to put things together. Once all the circuit boards and mechanical parts and everything are all completed and tested, then everything has to be put together. Once the finished assembly passes the visual inspection, then it comes into an automatic computerized testing procedure where all the different voltages and levels and various and sundry aspects of the board are checked with an automated computer program. These are called a Faraday cage or a screen room, where they are shielded from radio signals so that all the wireless equipment can be tested and critical measurements can be made without interference. This unit is used for outdoor training for emergency, search and rescue, auctioneers, band directors, all kinds of people, where they want a wireless microphone that gives them several hundred feet of operating range.
This is brought in to us received. Paper is loaded on a turn stand. As you can see, one is unwinding while one is not. It's going up on the top where it is split into its sizes prior to being folded. It drops down inside the machine where you can't see right now. Those are your cores that we manufacture. This is hot glue. There's different types you run on this. Cold glue sometimes, different formulations. This right now is hot. We run the glue at about 195 degrees. Right, jumbo rolls, anywhere from a 6-inch, 8-inch, 12-inch. Now it's going to drop a core down. Machine will come over here and cut the paper. Left side rolls and get rid of it. It starts now to roll the paper on a new core, like you saw earlier. It's a little bigger core. It's going to speed up, get up to the diameter that we dialed in, so we know how many feet is on there. And then it'll slow down, take the roll out. This is a combination of pneumatics, electric drive motors, air regulators. There it is, and as she comes out, now your first cut's a donut or a cookie. These salads you see in commercial institutions, restaurants, hotel kitchens, that type of stuff.
All this equipment you see has to be dreamed by somebody, designed. The idea has to be thought of using education, learning how to apply the education, drawing it, envisioning it, make it work. That's what education is all about. That's what dreaming is all about.
Motor station printer. You got your yellow, your red, and your black. Printing whatever the design is at the time. We're looking at 572 bags a minute. Quality control, the name of the operator and the date it was made.
$3,500 of toilet paper right here.
That is cutting each one. It's a massive rotary blade. The product is conveyed over to two wrapping machines. Wrapped up with whatever the paper wrap it is. In this case, we have the roses, red roses. It runs back down the conveyor. Went down, now pushed them in, come out, tilt the box over, and go out and seal it. Years ago, this used to be about a probably 3 or 4 person process. Doing all this by hand.
Think of the incredible amount of stuff made out of plastic. Here's how it's made.
Right now it's cooling. It's got a cooling, that's what all the hoses are for. It's got water. You set certain temperatures for certain materials. And the reason why they do that is for in efficiency, to do with economy. This requires not to have an operator come and cut it. These two parts are not the same, but they come out at the same time. You know your perfume cologne dispensers in laboratories, it's what holds those units together. And these go like this. You squirt, reload. This was a test run. As you can see, we got little dimples right there. He was off a little. His calculations are off by probably 10 thousandths.
That's what pushes the part out of the mold.
Creates a vacuum up there. It's got a little motor. Creates a vacuum, bringing up the raw material, which usually comes like this in a pellet form. This is when it starts getting into a molten stage. That tip will line up into that orifice. So that seats off on that so it won't leak. That will probably be on 3 million units a year, these buttons. Just to give an idea how heavy the tungsten is, this little square is no more than an 8" by 8" with the center cut out, still weighing about 150 pounds.
The cost of these 6 pieces of super hard tungsten material? $200,000.
This is probably the most precise measuring instrument you can use. It's got a probe right here where you come in and touch at every point. You can measure any part on this table.
Just about everything that Mega manufactures starts with steel plate, and we cut and form the steel plate into shapes, like these shapes you see around us, and we use press brakes, rolls, shears, and so forth. set plate on that table. And when you use either plasma or gas torches to cut the plate into the shapes that we want. And the reason water is used is to both control the smoke and emissions from the process so you don't get it out here in the environment, and also to cool the material so that we don't change the mechanical properties of the steel in the area where we're cutting. All of these products are water haulage tanks. Most of them are off-highway type tanks. And typically we'll spend about 30 days working on a project. Some of these tanks, even though they're on the outside, they look like a big empty shell. On the inside, there is quite a bit of structure and detail. A lot of that structure on the interior is there to keep the water's motion from affecting the ride of the vehicle. This is a piece of the inside of a tank. This piece right here is actually the tunnel that forms the backbone of this tank. Before they're painted, we blast the tank to remove the scale and corrosion that's on the steel. Well, these three sections here are all combined to form one tank. The reason there are three sections is to allow us to transport them over the highway. And then they go to a customer's location where they're put together and installed onto a large 240-ton mining truck. So this is getting closer to a finished product. You've got a scraper tractor drawing or pulling a water tank. This particular tank is what we call a drop tank. That arm there, draft arm, allows that tank to move up and down. The largest tank we build is about 5 times larger than this one, actually. We build all this product here. This is a mobile pump. It's an engine-driven water pump mounted on a trailer. These are on-highway water haulage trucks. These are 2,000 and 4,000 gallon units. These happen to be mounted on Freightliner chassis.
Out of this little factory come products sold nationwide in such stores as Walmart, Costco, and Home Depot.
The inspiration to Earthstone was actually trying to solve an environmental problem of pumice mining. This is a shot taken from the air in the Jemez Mountains of an active pumice mine. For $2.85 an acre, you can pretty much strip mine and leave it like this second shot. Without any topsoil, you've got runoff into the rivers and siltation. So the original inventor wanted to solve this problem, so he started making a synthetic pumice made out of recycled glass.
So the product is made out of about 98–99% recycled glass. And we crush it into a flour-like substance, so it comes out in these big super sacks, just like flour. So it's just like baking a cake. You start with the raw ingredients, and I have to mix a foaming agent within 100% of glass, 98% glass. So the mixing happens here in this mixer, and you mix what would be the foaming agent, kind of like the yeast in bread. The mixture gets deposited into these saggers, so the powder is about this deep, and it foams in the kiln up to about 8 inches. So like when you're baking a cake, you need a release agent, or like butter in the pan so that the bread will come out. So here we spray a liquid talc in the sagger so that we can pull the product out afterwards so that it's easy to release. All right, this is the oven where we get to bake the cake. Foam the glass, and it takes, about 12 hours approximately. This is our controller that controls the kiln, and it records each firing. It goes through a sintering process where it becomes very hard and dense before it foams, and the foaming actually is pretty brief once it starts foaming. And then it takes a while to cool the product because you don't want to cool it too quickly. And we pull it out of the kiln and then place it over in this cooling layer so that it can cool down on its own time. So this is where we take the product out of the saggers and they turn into these blanks. That powder is now foamed to this, which is fairly lightweight. So we cut our blocks into quicksand, is some of the products we make for sanding, which it conforms as you use it. And you always have a fresh surface. And you can do it much faster than you do with sandpaper. For instance, see how it conforms to the shape of whatever you're sanding? And you can use this to get into the tight areas like this. This is called grill stone for cleaning grills. And this is a floor tile with paint and rust and tar. It's a really terrible mess, worse than most people would ever have. You're using physics rather than chemistry to get something clean. Okay, this is called Rust Away for removing rust from metal.
Tool and die making is the process that underlies much manufacturing. Here, prototypes or trial parts are created for use in manufacturing everything from motorcycles to planes to cell phones. Much of the traditional hand-operated machinery has now been replaced by computerized machining.
Okay, the process of making a part starts out usually with a blueprint, and sometimes it comes across as just an electronic drawing. So we can receive an electronic file and import it directly into our computer. So I'll do a little demonstration. And hopefully what you get over on the computer is what you get over on the machine. This is called a vertical machining center, and if you look inside you can see the tool carousel, which is lined up with all the tools you might need for a particular job, and the machine will automatically change your tools when it comes time to use them. Now you can see the pocket's milled all the way through and it's doing a couple finishing passes on it. This is a part that we're making for Boeing right now. These machines are able to operate unattended. Everything will happen based on what the program tells it to do, and human doesn't really need to be around during the program. Everything takes place on its own. Now it's spot drilling, and the next is going to drill holes and do counter bores. Oftentimes a part has to be sent to a number of different machines before it's completed all the way done. Obviously you can only do so much from one side of the part. Oftentimes you have to drill holes from the sides or from the back side. That's the swing arm for a prototype motorcycle we're building. Started out life as a 150-pound solid block of aluminum and was all machined away until you have this part, what you see left, which weighs about 10 pounds. That's the strongest kind of part you can get is billet machined part. This machine's called electrical discharge machine, or EDM for short. And it uses 10 thousandths thick or 12 thousandths thick wire to actually do the cutting. And what it basically does is the wire has an electrical current through it which discharges and it burns the metal away. And the unique thing about it is because it's cutting with the wire, you can cut parts that otherwise would be impossible to mill out with an end mill. This little part here is kind of unique. Is I don't know if you can see, it goes from being a rectangle to a smooth transition to a round hole at this end, and that's something that you can only do with a wire ADM because it's, you know, there's no way to mill something like that.
These cuts are made with the wire EDM to create this thin flexure, which gives this part an axis of rotation. This part also is a flexure with flex designed into the part.
Round parts are something that you would produce on a lathe because you can typically get better finishes and it's more efficient to run round parts on a lathe. These are for Sumitomo, which is a company that manufactures silicon wafers for the semiconductor industry. The program these machines run on consists of lines of coordinates. X and Y are your simple Cartesian coordinates, left to right and back and forth, and Z being the vertical axes.
Let's watch the designing and building of a prototype for a high-tech optical device and the assembly of an actual product.
We start with the optical design, characterizing the optical performance of what we're trying to do. Then we start looking at the mechanical design, building structure around the optical components in a sort of a rough fashion in order for us to have a starting point when we move to our mechanical CAD program. Of course, this is a prototype. We'll gradually move and refine this design to be more of a production version. We can now show you how we move this from the idea state to the actual manufacturing of the first prototype. The centerpiece is called Pyramid Prism. That allows us to split basically the light into 4 identical paths, and then they'll get formed an image onto 4 cameras. In this case, is 4 identical cameras. So let me go ahead and get this guy out of the chuck, and we'll go ahead and put this system together. In the mechanical CAD program, we had, actually in that case, there was 4 of these in the back. Just for this purpose, we're just putting 1 on. All right. The next step would be to put a camera on the back of this and to then test it out for its performance. Another optical device that this particular one gets mounted to a microscope, and it allows scientists to do different things on the cellular level. And the idea that scientists are looking at is they want to be able to tag different parts of the cell different colors. So one part of the cell might be tagged with a green dye, and the other side of the cell might be tagged with a red dye. So how it works is the device attaches to a microscope, screws onto the microscope port here where you normally would screw a camera. This is the camera that we use for what calibration of this particular instrument. And it allows you to turn the photons that travel through this microscope into electrons and then read them into a computer. And right now we're looking at basically 2 identical images, where the left-hand side is actually identical to the right-hand side, other than it's a different color.